Okay, so we're going to be talking about molarity and dilutions today, like I said. So we're going to go ahead and define what molarity and concentration are, because we're going to be using concentration in our calculations. So that is what this first blank is for. It is for the word concentration. Okay. Concentration refers to the amount of substance per some defined space. It's the amount of stuff that is in a given volume, essentially. And on our solubility curves, we express concentration in terms of grams of solute per 100 grams of solvent on those y-axes, as we saw last class. When we start using solubility in some of our problems, as you'll see here today, we rarely express concentration in terms of grams of solute per 100 grams of solvent. Instead, we like to use molarity. So molarity is what we are going to dive into today. Molarity is defined as the number of moles of a solute per liter of solution. Okay, so you can see the equation for molarity is going to be N referring to the solute. This is going to be referring to moles over liters. And so that's what you're going to see on your formula chart. You see that molarity is equal to moles of a solute, or lowercase n, over liters of solution. Typically, we express this per 1 liter of solution. So, your molarity can also be solved for by taking the mass of the substance, the solute, in the solution, and dividing its mass by its molar mass, and then dividing all of that by liters, because mass divided by molar mass is also what will get you moles, okay? So you can substitute, you can make a little note, you can substitute mass over molar mass for moles if you so choose, because they are the same thing. Dividing the mass of something by its molar mass will get you the moles of that substance. And our units for this measurement of concentration are going to be moles per liters, which is what we divide by here, moles per liters, or just capital M. So please be familiar with both the moles over liters and the capital N. They are interchangeable. And you will need to know that for later problems that we do today in class. Okay, so for example, if we had 2 moles of a potassium nitrate substance dissolved in enough water to make 1 liter of total solution, we would say that the concentration of that solution is 2.0 m, or 2.0 moles per liters. We could also say that it is 2.0 molar, that we had a 2.0 molar solution, okay? So that is how we would express concentration in terms of molarity. Bless you. Molarity is going to be our most common way of expressing concentrations in solutions, so we do need to know how to interpret it. If we say that there has been an increase in molarity, we mean that to say that the solution has become more concentrated. An increase in molarity means that the concentration of the solution increased. The solution is more concentrated. So that goes with increase in molarity. A decrease in molarity, on the other hand, a decrease in molarity means that the solution has become more diluted. More diluted, or less concentrated is another way to say that. But you will often see it referred to as a dilution, or it will have, the solution is said to have been diluted to make it less concentrated. So that corresponds to a decrease in molarity. So make sure you have that written down. The next thing we're going to talk about is how you can actually prepare a solution of a specific molarity. So to prepare a specific molarity solution, you have a couple of steps you need to follow and specific equipment to use. The one thing I want you to notice over here is that you need a volumetric flask to prepare your solution accurately, to prepare it precisely and accurately, okay? You always want to use a volumetric flask when you are preparing solutions. This is how I prepare y'all's solutions before labs. If you have a lab and you had to have, 1 molar solution of some specific type of solution, I would use a volumetric flask to create that, okay? And I want you to be familiar with how solutions are prepared from the components that make them up, the solute and the solvent. And those steps are listed right here. We have to calculate how many grams needed to correspond to the number of moles of solute we need. You would mass out that many grams using an electronic balance and a weigh boat. You would add that amount of solute to your volumetric flask, and then you would add distilled water up to the line of the volumetric flask, because remember, volumetric flasks are that weird piece of glassware. They're shaped like this, and they have one little marking on the stem that corresponds to their size. You can have lots of different sizes of volumetric flasks. You can have 1 liter, you can have 500 milliliters, 250 milliliters, so on and so forth, okay? So that is how you would prepare. You would mix that up, you would cap it, and then you would invert it and mix it up, okay? So how many grams of sodium hydroxide must be used to make 500 milliliters of a 2.5 molar sodium hydroxide solution here in this example? We could calculate that, and then we can describe how we would go about preparing this solution in the laboratory using what we learned up here. So how many grams of sodium hydroxide must be used to make 500 milliliters of a 2.5 molar sodium hydroxide solution? Well, we just learned up top that we can calculate different variables in a molarity problem using these equations. Since we're talking about mass, we want to know how many grams there are. I'm going to go ahead and grab this equation, this mass over molar mass, all divided by liters equals molarity equation, in order to try and figure out the mass that we would need. So down here, I'm going to write that molarity equals mass over molar mass over however many liters you have, okay? So liters, it's important that your volume is in liters for molarity. I also think it's beneficial to write out everything you know off to the side on your problem. So we are told, we're trying to figure out the mass of sodium hydroxide needed to make this. So I'm going to put, question mark number of grams. We don't know how many grams we need. We're going to try and figure that out. We do know the volume. We were told the volume was 500 milliliters. And we know the molarity is 2.5 molar, or 2.5 moles per liter. And so we're trying to solve for mass. The only other thing that we don't have is the molar mass. So we need the molar mass of sodium hydroxide. So I want y'all to go ahead and calculate the molar mass of sodium hydroxide. This would be a good time, if you don't already have your blue periodic table out, to go ahead and grab your blue periodic table. So you need this guy to help you calculate the molar mass, and yours is blue. So go ahead and calculate that, and then try and plug in your values and solve for the mass. Okay, y'all? I'm going to give you a couple minutes to try and solve that out, and then we'll go over it. Okay, could anybody raise their hand and tell me what the molar mass of sodium hydroxide is? Yes, ma'am. 40. It is 40. And do you remember what the units are for molar mass? By any chance? Grams per mole. Very good. Grams per mole. Grams per mole. So we know that the molar mass of sodium hydroxide is 40 grams per mole. And then we have all these values that we can now plug into our equation that we are given here. So 2.5, you know, this is moles per liter, essentially, is equal to our mass, which we don't know. We don't know our mass. I'm just going to put a little question mark there. Over, or I guess we could put X, but I'll just put a little question mark for now. 40 grams per mole all over our volume, but we want our volume to be in liters, okay? So how would we go about converting that 500 milliliters to liters, y'all? You could use dimensional analysis, exactly. How would we set up that dimensional analysis? If we had 500 milliliters, what would go on the top, what would go on the bottom? What would go on the top, y'all? 1. How many milliliters are in 1 liter, y'all? 1,000. I heard somebody say 1,000. So that's where your 1 times 10 to the 3 could be put. You could put 1 times 10 to the 3 down here, or you could put 1,000. That's how many milliliters are in a liter. So we're just essentially dividing this by 1,000, which would give us what, y'all? 0.5. Exactly. So we would get this, 0.500 liters.
I thought the one that was in prefix.
Yes, you could put the one with the prefix if you wanted to do this with your prefixes. You could do 1 times 10 to the negative 3 liters over 1 liter. Because we know that there's 0.001. If you do this here, you can get the same thing. 500 divided by, here you go, 1 second EE to the negative 3. Or, I did this wrong. I'm so sorry, y'all. You put your 1 with the prefix correct, and then you put your 1 times 10 to the negative 3 up top. Apologies. So yes, so if you wanted to use your prefixes from your formula chart, you could do 500 times 1 second E to the negative 3, and that would also get you your 0.5 liters. So if you know that there are 1,000 milliliters in a liter, you are welcome to do that. If you are somebody who would like to fall back on the prefixes, they are all included here on the bottom right on this side of your formula chart. Okay? Any other questions there? No? Okie dokie. So we're going to go ahead and plug that value of our liters in right there. And so hopefully y'all were able to do the 2.5 times the 0.500 and then solve for your mass by multiplying the product of these by our 40. Can somebody tell me what they got for their answer here for the mass? Anybody? 50, yeah, it is 50. So it is 50. And I'm going to go ahead and put a little decimal there. So it has 2 sig figs. Why did I make it so it has 2 sig figs, y'all? The least amount of sig figs. Yes, exactly. So this guy had 2 sig figs. That was the least amount in our givens. We had 3 sig figs here, so we want to go ahead and make our answer 2 sig figs. So we know that we need 50 grams of sodium hydroxide to make this amount of 2.5 molar sodium hydroxide. Okay? What questions do we have about that? Yes, sir. How did I get 50? So I did my 2.5 times my 500. You take that, and then you will, or times my, sorry, I did that wrong. 2.5 Let me make it a little bit more visible for y'all into the camera. 2.5 times our 0.500, and then you multiply that by 40 because you're solving for mass over 40. So to get that out of the denominator, multiply both sides by 40. You will get the 50 there. Any other questions? Yes, ma'am.
In the right-hand corner, the grams of milliliters, do you have to put the units or
I like to put the units because it helps me make sure that all of my units and my numbers agree with one another. Like right here, I have liters over here, and I have liters over here. So I know that those are going to cancel out. And I have moles here, and I have moles over here. I know those are going to cancel out and leave me with grams. So I would recommend putting the units just so you don't end up in a situation where you forget to convert your milliliters to your liters there.
so you don't have
Okay. So any other questions? Okie dokie. Awesome. So we know how many grams we need to make that solution, and now we want to write about how we can go about preparing this solution in the actual laboratory. And we could follow our steps that we have up here. So we've already done step 1. We calculated how many grams of our solute we need. Step 2 is to mass out that many grams. If we had some sodium hydroxide in a container, we would go ahead and we would mass out our 50 grams of sodium hydroxide. What could we use to mass that out, y'all? A balance. We could use a balance. And we would also probably use a weigh boat because we don't want to just put our sodium hydroxide directly onto the balance. But definitely we're using that balance along with the weigh boat. Our second step here, since we've massed this out, is to then add the amount of solute we mass to a volumetric flask of the size corresponding to the volume we need. So we're going to put our 50 grams of NaOH into a volumetric flask. What size volumetric flask should we use, y'all? How much of this solution do we want to make? 500 milliliters. So I would go ahead and use a 500 milliliter volumetric flask. If you want to put, 0.5 liter volumetric flask, that is also fine as well. And then the last thing you're going to do is you're going to add water to the line and mix. My pen is trying to give out on me. I will switch it here in a second. We're going to add water to the line and mix. So that is how we would prepare that solution and how to figure out how much we need gram-wise. Cool. Let's flip to the next page then and start applying. So what I want y'all to do here, I want y'all to use what we just did. I want you to use your, molarity equals mass over molar mass over liters, your equation, to help you solve these problems. Again, I think it's helpful to write out what you know off to the side. But if you feel you can plug in your values without doing that, I'm not going to make you write those out. I just think it's beneficial. So we're going to spend some time working on these, and then we'll go over them here shortly. I'm going to start going over these. So for this first one, I see that, we're looking for molarity, right? The molar concentration. So we're going to need a couple of things here. Can somebody raise their hand and tell me the molar mass of lithium hydroxide? Yes, Gabby. 23.95. Do we agree with that, y'all? Yeah, that is correct. Very good. 23.95 grams per mole there, right? And is there anything else I need to do to all my values that I know before I start plugging stuff in? The milliliters, what about it? It should be liters. What's that going to be in liters, y'all? 0.75 liters. Very good. So now we can hopefully just plug in our values, plug and chug. We're looking for the molarity. We know the mass. We know the molar mass. And we know the liters because we just converted. Would somebody like to raise their hand and tell me what they got for the molarity? Anybody? Yes, 1.99. 1.99. So, you should have 35.8 divided by 23.95. And then you divide that by 0.75. You should be able to round that to 1.99, like she said. And then you can put on that M. What's the other way we could write this unit, y'all? Moles per liters. Moles per liters. So if you put capital M for molarity, molar, or moles per liters, that is the correct unit. You just do need a unit there, so make sure you include that. Okay, very good, y'all. The next one, our molarity, we knew this. 0.500 moles per liters. We knew our mass of 40 grams. Can somebody tell me what the molar mass of sodium chloride is going to be? 58.44. Yes, yes, yes. 58.44. And all over our liters, which we do not actually know, so I'll just put that as X. If you solve for this value, how many liters do y'all get? 1.36. Do we agree with that, y'all? Round it different? So I'm going to do 40 divided by this real quick. Let's see. 40 divided by 58.44. And then we divide that by 0.5. What could I round that to? 1.37. Y'all were close. 1.37, okay? 1.37 liters. What did the question ask us for, y'all? Milliliters. How many milliliters? So how many milliliters is this, y'all? 1,370 milliliters. Very good. Any questions there, y'all? Okie dokie. Then we're going to move into dilutions or dilutions. Dilution is the process of making a solution less concentrated. We mentioned this on the previous page of notes. If you make something more dilute, you make it less concentrated. This is usually done by adding more solvent to our solution. So looking at examples A and B here, can you discuss with your groups very quickly which one you think is more concentrated and which one you think is more dilute?
More concentrated A.
What do we think, y'all? I want you to hold up a 1 for A and a 2 for B. Which of these solutions do you believe is more concentrated? 1 for A or 2 for B? 1 for A. Yes, it is indeed A. Why do you think it is more concentrated? Why does it seem more concentrated to you? Yes, Max. The molecules are packed closer together. Yeah, look at these guys. In A, they look much more closer together than B. That is definitely more concentrated than B. Very, very good. And then the second one, more dilute, obviously B there. So if you were to look at these two solutions here, which of these would you say has the higher concentration, or it's not the higher concentration, the higher molarity? Yeah, 1A, right? So this guy is going to have the higher molarity because that's the definition of molarity is concentration, right? So the more concentrated, the higher the molarity. This one's going to have the lower molarity. And so typically what you can do is you can adjust the concentration of something by changing something about the solute or the solvent. What does it look like we did from A to B to make this more dilute? What did we Yeah, did we take out solute or did we put in more solvent? We put in more solvent, okay? So in this specific case, this became more dilute because we added solvent here. So if this was a solution of, say, like water and salt, what we did is we added more water. We added more solvent, the thing that is doing the dissolving. So we usually use molarity and dilution problems, which we're about to tackle right now. It's the most common way to express concentration, and when we do something like add more solvent, as we said is probably the case from here to here, we decrease the concentration of the solution when we add more solvent. Increasing the amount of solvent decreases the concentration of the solution, which will decrease the molarity of the solution and makes the solution more diluted. So you want to make a solution more dilute, you can add more solvent. And we are going to deal with some dilutions mathematically here in the next three examples that we cover. The next three examples, each one is a slightly different type of dilution problem. So there's going to be some slightly different things you're going to have to use to solve these. The first one is probably the easiest one, and then the next two are a little bit more tricky, okay? So what we use when we solve dilution problems is we use this equation V1 times M1 equals V2 times M2, or VOOM for short, because it's, VM. So in this first example here, we are asked what is the molarity of a solution, okay, what is the molarity of a solution of an ammonium chloride solution prepared by diluting 50 milliliters of a 3.79 molar ammonium chloride solution to a final volume of 2 liters. So what is going to be important when you do these dilution problems is making sure you organize your information. I like to put little notes in the actual word problem so I can distinguish between the values and I know which ones are my V1 and my M1 and which are my V2 and my M2. You will have to solve for one of these variables in these equations. And what you're going to do is you're going to be careful to keep the volume and the molarity that go together. What I mean by that is when you are told, for example, that you are diluting 50 milliliters of a 3.79 molar solution, this volume goes with this molarity, and then we are going to make a solution that has a final volume of 2 liters here. So what I also like to do, I like to make these 1s and these 2s. I like to make the 1 my initial and the 2s my final, essentially. So I know I'm starting out with this volume and this molarity. So I'm going to label that V1 and this M1. And then I have a final volume of V2, and I'm trying to figure out what my final molarity is going to be. We just don't know what that is. That's what we're trying to figure out. One other very important thing you need to do, besides make sure you keep your volumes and your molarities together, is you need to make sure that your volume units agree. For example, here in this problem, I see that I have one volume that is in milliliters, and one volume that is in liters. Since we are essentially setting up a ratio here, I'm going to need you to go ahead and make sure that you include agreeable units. So, or I'm actually going to leave a little bit of room. It doesn't matter which one you convert to. You could convert this to liters. You could convert this to milliliters. I'm just, for this problem's sake, I'm just going to convert this one to milliliters. It would not matter if you converted this to liters instead. The same outcome, you would get the same outcome, the same answer, okay? But what I want us to do is we want to make sure that our units match. The units must match in an M1, V1 problem. But now that our units match and we know what we're solving for, M2, we can just plug this into that equation. So it's just plugging in and solving algebraically, okay? So we know V1 is 50 milliliters. We know M1 is 3.79, bless you, molarity, or molar, bless you again. And we know that our V2 is 2,000 milliliters. Again, I like to include my units just so I don't accidentally forget to not convert, or accidentally forget to convert. I did a double negative there. So including the units helps you remember, hopefully, to convert there at the end. And then we can solve for M2 here. So go ahead and solve for that. Practice typing that into your calculator. Make sure you include the proper unit on your answer. And be mindful of the sig figs as well. Would somebody like to share what they got for their answer? Anybody in a sharing mood? I'll share what I got. Here's what I got. Could somebody tell me what they'd round that to make sure that the sig figs match our 3 sig figs in our problem? Yeah, 0.0948. Perfect. So yes, this 0 does not count as a sig fig. It is, we only start counting at the 9, so 1, 2, 3. And what is our unit for this, y'all? What? You can just put capital M. You could also put moles per liters. Either one is acceptable. Indeed. What questions do we have about that problem? Do we have any questions about that problem? Yes, I can. So the question was, can you explain again how we know which ones to label, V1 or V2 or M1, M2? What I usually do is, again, I usually think about V1 and M1 as my starting solution. And so I'm like, okay, I'm diluting this much of this solution. So I'm starting out with this much, and then I'm diluting it to a final volume of this. So I'm treating this as my final, and this is my initial. But if you have this phrase, this whole other phrase, that is basically this is this volume that goes with this one. If I had switched these and made this V2 and M2, and then I made this V1 and this M1, my answer would not have changed. It's just the positioning, really. So, bless you. It's very important that you just keep the volumes and the molarities that go together. And so if you see something like an of a phrase, these things go together. Does that make more sense? Yeah? Okay. Any other questions? Okay, then let's move on to the next problem. The next problem is not too much more difficult than this. Same concept. It's just they're a little bit tricky with how they are including the volume in the problem. They give you all the information you need, but it might not seem like it at first. So here in this example, we're told that we have 1 liter of a 3.8 molar solution. So a 1 liter, 3.8 molar solution of iron 2 sulfate has 7 liters of water poured into it. What is the molarity of the new diluted solution? So again, we're looking for the molarity of the new diluted solution. So this volume and this molarity go together. So I'm going to go ahead and, label this V1 and this M1. We're looking for the molarity of the new diluted solution. So I'm going to go ahead and put M2 there. Okay. So this is what we're solving for. We don't know what this is. And so we have V1 and we have M1. We also need V2 because our formula is voom voom, V1 M1 equals V2 M2. We need a V2. And so you are actually given the V2 in this problem. You just have to do a little bit of math to figure it out. You are told all the information you need. So take a second to talk about your tables, how you would go about getting the V2 value, perhaps. Okay, let's talk about this. Can anybody tell me how they could go about getting that V2 value? Adding what? The 1 liter and the 7 liters, right? You can add those two together. We said that this 1 liter, 3.8 molar solution had this much water poured into it, right? So V2 is equal to this plus this, right? The final solution is going to be the 1 liter plus the 7 we poured into it. So we're going to have 8 liters of water. Very good, y'all. That is our V2. Do our units match for volume? They do indeed. So now we can plug it in and solve it. So that's what I want y'all to do. Plug it in and solve it. Make sure you include a unit on your answer. Okay, what'd y'all get for the molarity? And D. So hopefully you got this. 0.48 is, if you have the unit on it, then that's fine. But you need the unit, otherwise you get half a point off. So molarity is always going to have the unit capital M or moles over liter, either one. Just make sure you do include a unit, no naked numbers, please. Okay. Any lingering questions there before we do this last one? This last one's a little bit different. Slightly tricky. Okay, so this last example before we get into reaction stoic with molarity is going to ask us to prepare 500 milliliters of a 2 molar solution from a stock solution of 6 molar hydrochloric acid. So, what we have, y'all, is we have a stock solution of hydrochloric acid. Stock solution, this is just how chemicals come shipped, okay? If I'm trying to prepare a solution of hydrochloric acid for a lab, for example, if I'm trying to prepare a solution of like 0.35 hydrochloric acid, 0.35 molarity hydrochloric acid solution, I can't just go to Flynn Scientific and order 0.35 molar hydrochloric acid. What they do is they ship it to us in stock solutions such as a 6 molar hydrochloric acid, which is very, very concentrated. Okay? And so what we have is this value. I have this, so this is going to be, I'm going to just assign this M1 as what I have. I have this value, okay? But I want this volume, I want 500 milliliters of a 2 molar hydrochloric acid solution. I don't want 6 molar hydrochloric acid. I want 500 milliliters of 2 molar hydrochloric acid. So this is what I want. But this is what I have, okay? Is the solution that I have more or less concentrated than the solution that I want? Yes, the solution that I have is more concentrated than the solution that I want. So what I need to do here is I need to dilute this. Okay, I need to dilute this solution. And how you do that is a little bit strange. It seems a little bit strange. We are going to use VUM. So we are going to use this V1M1 equals V2M2 equation. And I'm going to plug in these values as M1, V2, and M2. So V1, don't know, how much I should start with, but I do know that it is 6 molar. And I know that I have a volume of 500 milliliters over here. And 2 molar that I want here. Okay. So calculate V1. Can y'all show me with your fingers how many sig figs our answer should have? It should have 3. So there's a little decimal right there. 3 and 3. So these all have 3 sig figs. So what could I round my V1 to, y'all? What could I round this to? 167. So 167 milliliters. Okay. Any questions so far? Okay. So what we do with this knowledge here is, in order to make a dilution, to dilute this concentration down to 2 molarity and to 2 molar, and to make 500 milliliters of it, what I'm going to do is I would measure out 167 milliliters of my 6 molar HCl solution. Okay, I'm going to measure out 167 milliliters of this. I could do that with something like a graduated cylinder. Okay. Once you have measured out that amount, you are going to put that, similarly to how we talked about making solutions earlier in a volumetric flask, we are going to put that amount of 6 molar HCl into a 500 milliliter volumetric flask. Okay? We want to make 500 milliliters of a 2 molar solution. So we're going to get ourselves a 500 milliliter volumetric flask so we can make 500 milliliters of a solution. In order to make that solution, we need 167 milliliters of 6 molar HCl, which we put into the flask, and then we need to add water up to the line. We're going to add water up to the line, and we're going to mix them together. So technically what we do here is we add in 333 milliliters of water We add 333 milliliters of water into the 500 milliliter volumetric flask, along with 167 milliliters. In total, we're going to have 500 milliliters, okay? I don't want to make more than 500. In order to make 500 milliliters of this concentration, I need 167 milliliters of this and 333 milliliters of water to dilute it. And that makes sense because we're starting out with something that is a higher concentration, and we want something of lower concentration. So we're going to have to add some amount of water in to get it to a lower concentration. To figure out how much water that is going to be and how much of that is going to be the hydrochloric acid solution, we can use our Voom Voom. What questions do y'all have about that? I do want you to be familiar with this process. Hint, hint, nudge, nudge, kick in the face. Yes? Oh, great question. So the question is, in step 2, is it you're pouring in the 2 molar? No, it is the 6 molar HCl, because that's what we're starting with. So we're trying to make this, so we have to measure out 167 milliliters of this, and then we put that amount into your 500 milliliter flask, and then we add water in and mix it. That water will dilute that 6 molar HCl down to 2 molar.
So I can measure that and then put it in.
Yes, correct. Okay, any other questions there? Okay, then the last questions we're going to go over today are reaction stoic questions. I'm going to try and make this as straightforward as possible. So, because molarity involves moles, remember that molarity, remember the other unit for molarity is moles over liters, because that's what molarity equals, moles over liters. If you do this divided by this, you get the molarity of something. Since molarity involves moles, we can use molarity in the context of stoichiometric problems. Molarity can either be calculated by finding moles using stoichiometry and then dividing it by liters, or it can be used as a conversion factor, okay? It can be used as a conversion factor. Let me find here's my highlighter. So we can use it as a conversion factor because molarity is equal to the number of moles over liters. Number of moles over liters can be interpreted as a conversion. Number of moles equal to 1 liter. How many moles are in 1 liter of a solution in essence? So we can use molarity as a conversion factor. I'm going to show you how to do that in these calculations here. And since we are looking at some reaction stoichiometry problems, we also need to remember how to write out reactions. We need to know how to write out reactions. So we need to remember our polyatomic ions and how to, for example, do a double replacement reaction. So for this first example, y'all can do it. You can do it. I believe in you. We are told, we want to figure out how many milliliters of 0.15 molar potassium iodide solution would be required to react completely with 15 grams of lead-2 nitrate. The first thing you do in this situation is you write your reaction, okay? Potassium iodide is reacting with lead-2 nitrate to form 2 products. So I need you to write potassium iodide plus lead-2 nitrate and then draw your arrow and then write your products, okay? So like potassium iodide, that's potassium iodide, okay? I want you to write out the formula for lead-2 nitrate. I'm leaving space so we can balance it at the end. I want you to write the formula for lead-2 nitrate, and then I want you to write the products. So go ahead and do that. If you get bored, you can write the neutralization reaction down here too before we talk about this. Or you can try and puzzle it out yourself if you get ahead. But first, write that equation and balance it. Okay, so can somebody share the formula for lead-2 nitrate with me? PbNO32. So should I write it like this?
32.
Parentheses around what?
NO3.
NO3, yes. Make sure you have a parentheses around your wonderful polyatomic ions if you have more than one of them. But there is lead 2 nitrate. Very good, y'all. So what's one of the products we make over here, y'all?
Lead iodide.
K, what? NO3. Very good. KNO3. And what's the other one? PbI2. Very good, y'all. So, there is our equation. Can anyone tell me what the coefficients are for those guys? 2, 1, 2, 1. Very good. So I'm just going to leave those blank since that's understood as 1 if it's blank. Okay, so what we have here is our balanced equation. And we want to know, how many milliliters of this molarity potassium iodide solution are going to be needed to react completely with 15 grams of lead 2 nitrate. Okay? So, 15 grams of lead 2 nitrate, and we want to know how many milliliters of this molarity solution we need. So, we can actually do this whole problem with just dimensional analysis. We can go from grams of this to moles of this, so that way we can start changing substances. Do y'all remember what we used to get from grams to moles? Molar mass, molar mass. So I can get grams to moles, and then the next thing, going from moles to moles, then you can use the mole ratio, okay? And then we can actually get from moles to milliliters in a couple of steps here, y'all, okay? We're in moles of potassium iodide here. We can get to milliliters because we can actually use the molarity of this substance. We can use the molarity of this to get from moles of this to liters. Because what this is saying, remember this is moles per liters. This also means the same thing as there are 0.150 moles per 1 liter of potassium iodide solution, okay? That's what that means. So we can go from moles to liters by using this conversion factor, and then we know we can get from liters to milliliters by dividing by 1,000. Okay? So we can do this all in one go, dimensional analysis. I'm going to start it over here. I'm going to make sure I label my substances. 15 grams of lead 2 nitrate. Okay, I'm going to use train tracks for this one. I'll use parentheses on the next one. Okay, so there's my train tracks. So we're going to have to use molar mass, so you do need to go calculate that. So that is on your formula chart. You can use that. My pen is on its last legs. I think it'll get us through this problem, though. So you'll need to calculate the molar mass. And then see if you can set up the rest of this problem. And we'll talk about it here in a second, because you have the map. Let's go ahead and fill out the rest of this. I went ahead and made basically the skeleton of it for y'all. So can somebody tell me what the molar mass of lead 2 nitrate is? It is 331.22. Very good. And so what goes up on top for that? 1. Perfect. There is this many grams of lead 2 nitrate per 1 mole of lead 2 nitrate. And then our mole ratio. What do we go look at to find the numbers for our mole ratio? The coefficients. Absolutely. So what we use to balance our equation, right? So what do we get to put with moles of potassium iodide? 2. What do we get to put with moles of lead 2 nitrate? 1. So 2 up there, 1 here. And then over here, This was our molarity conversion. And so what did I say we got to put with this mole here? 0.150, very good. And then what do we put with liters? 1, very good. And then what could we put here? You could put 1,000 here, and you could put 1, or you could put 1 and 1 times 10 to the negative 3 here. Either one is fine. I can make a little note. Or, 1 milliliter over 1 times 10 to the negative 3 liters. Either one of those would work. Okay? So, for our answer, can anybody tell me what they calculated here? So let's go ahead and do it. I'm getting a couple different answers. So what I would do here, I would go ahead and I just do 15 times 2 times 1,000 up here. Okay, let's just do what we put here. Okay, and then you're going to take these and you're going to divide by, and I'm going to open a parenthesis, 331.22 times 0.150 because everything else is a 1. You should get this value. Yeah, so this is why we put so much emphasis on the work you show, because if you do everything else right, you're only going to get half a point off for miscalculating in your calculator. But here, you would want to go ahead and round it to 3 sig figs, since you started with 3 sig figs here. So what can we round that to, y'all? 604. So 604, 603.8, round the 3 up to a 4. Okay. Any lingering questions there? Please show your work. Make yourself a mole map if you need to. These are obviously a little bit complicated. Okay. So there's your answer. The next one, you also need to write out the equation. So go ahead and write out your equation if you've not done so already. You have hydrochloric acid reacting with calcium hydroxide. Y'all, what is the formula for hydrochloric acid? It is HCl, okay? Hydro, and then the ic. That's just chlorine. It's not like chlorate or anything else. It's just H and Cl, okay? So do that with your calcium hydroxide. I'm going to have to switch pens. And then we will go over it. Okay, sorry, y'all, my pen decided to die, so I'm changing it to this one. Okay. Go ahead and write that out. Okay, let's go ahead and talk about this. We have HCl, hydrochloric acid, and then we have calcium hydroxide. I'm going to go ahead and just write out the skeleton equation here for the sake of time. Calcium hydroxide, and then we make water, which I like to write as HOH in double replacement reactions to help me balance. And you have calcium chloride here, okay? So here, writing water like this helps you think of it as an H and as an OH. And so how many OH do we have on this side? 2. How many do we have over here right now? 1. So put that right there, remember? And then where else can I put a 2 to make this balanced? In front of the HCl. Very good. That is the balanced equation. Okay, 2 H's on each side, 2 OH's on each side, 2 chlorines on each side, and 1 calcium on each side. Okay, so this one is a little bit different. We can't do the whole thing with dimensional analysis. We can do most of it with dimensional analysis. But we are going to rely, again, on the fact that molarity is equal to moles over liters. That is something we're going to need here, okay? We are told that 25 milliliters of hydrochloric acid with this concentration is neutralized by this volume of calcium hydroxide. We want to know what is the concentration of calcium hydroxide, okay? So we're trying to figure out the concentration of calcium hydroxide. We have the volume of calcium hydroxide because we can convert this milliliters to liters. So all we need now is the moles, so we can actually solve moles divided by liters for the molarity. So how we can do that is we can figure out the number of moles of calcium hydroxide, so that way we can plug it into this formula. We know that we have 25 milliliters of this hydrochloric acid with this concentration. So we're starting off with this many milliliters, and we're going to kind of go in reverse. We're going to go in the reverse direction, okay? Because you know, again, that this, remember that this means the same thing as this, okay? So make your mole map in reverse, bless you, based on what we did here, and then try and set that up, and then we'll go over it in the last 7 or so minutes before I let you get your phone, okay? So y'all can do that. I'm going to let y'all work on that for the next couple minutes. Okay, I'm going to go ahead and fill the rest of this out with y'all so that way we can check our work before class ends. So here I put a little extra little note here because I forgot to do this before I told y'all to go work on this. This neutralized bit here, that's just a reminder here that this means the mole of hydrochloric acid reacted completely with the moles of calcium hydroxide. Okay? So we essentially were working in reverse here. We were going from, you can go from milliliters to liters using, you can divide this, you can multiply this by, divide this by 1,000, sorry. Divide this by 1,000 to get to your liters, and then you can get to your moles using your molarity, like we just saw. And then we can go to, moles of this using our mole ratio. And I just realized that I put divided by 1,000 up here when it should have been times 1,000. Sorry about that error, y'all. It should have been times 1,000. But over here, going from moles to moles, we can go that way using our mole ratio. You can set this up. Hopefully you set up your problem like so. Again, I'm going to just kind of pop these down in here. Okay. And then you have your 1 liters. This is your molarity. Remember that this is the same thing as saying, we have this many moles per 1 liter. So you can use it as a conversion factor here, going from liters to moles. And then you can go from moles of hydrochloric acid to moles of calcium hydroxide using your coefficients. So we balanced our equation together earlier, so you knew you had the right coefficient. This will get you the number of moles of calcium hydroxide that react with this much hydrochloric acid. You should have gotten a large number a very, very small number like 0.0015425 moles here. Okay, this is what you go and plug in over here. Okay, so your moles, if you put this over the liters of calcium hydroxide, so 0.02345 liters of calcium hydroxide, you will get the molarity of your calcium hydroxide, which that should have come out, if you got this in 4 sig figs, it should have come out to this value. So that is your answer there. Okay? What questions do we have about that problem? Again, apologies for the error up here. It should have been times 1,000. Hopefully I didn't confuse y'all too much. Okay.